last time we argued about the security of web, and if you remember, we answered some questions about how secure is web and why, and how different things in web, such as the IV or the CRC, influence the security of web. And then we talked about 802.1x. You also experienced with this by solving an exercise, and this is still open until tonight. So at the kind of end of the day, and take care that all the time this exact timing, it depends on the timing of the server where the Moodle is hosted. And there are some differences, I know, from the last years. So never, especially for the exam, never leave the submission on the last minute. Even for the exam, you can send or resend the exam answers as many times as you want. So, and only the last one will be the one that counts for grading. So never leave it in the last moment, because you can just submit something and then at some other point in time, if you want to change, you can just, I don't know, resend. Okay. The same is for now. So take care. Officially it's by tonight. Okay. But don't leave it in the last moment. So if you still want to do that, you can still do it. There are 22 submissions by now. Perfect. So we talked about 802.1x. We talked about WPA, about the improvements of WPA over web, but also some limitations of WPA. And we will. Now I see that I put this twice. So I will need to edit this one. So today we're going to continue with this, but before continuing about with WPA, and we will look into the four-way handshake, and we will start with Kahoot, so you can prepare your phones or your computers for let's say understanding better some of the protocols that we talked about last time. Before starting doing that, and that we're going to pass over to WPA2. But before doing that, I want to ask if you have questions. If there's something you want to discuss before starting. No. Okay, so if there are no questions, I will start now the Kahoot. Okay, so you see now the code here. You already know from last time. You go to www.kahoot.it. You enter this number here. Also nickname. You think about the Halloween that is coming because of the background. And when everybody is joined, we start. Okay, that is cute. So we have a phantom with us. There are just 26 by now. We're more in the meeting. I will wait. We're 32 in the meeting, so maybe some others want to join. We wait a little bit more. Again, remember we will use this as an activity during the course. So again, the first one in the top will get 3 points. Second place 2 points. Third place 1 point.
Excuse me, could you
Yes.
repeat what is the deadline for the activity, because I totally forgot about it. And
Today at midnight. So you
today at midnight.
kind of midnight. So you can also do it. It's here. See, until
Yes.
night. So
Okay.
kind of midnight, 55, but 55 by the Moodle server clock. So, but anyway, you will have plenty of time to do it after the end of the course now. Exactly, that's why I left it until the end of today to remind you again for the course now.
Yes, I totally forgot. It's okay.
Yeah,
Thank you.
it's happening. It's not a problem. Okay. So if you want to do it, it's 5 minutes, not more. You will see after the course, especially that we talked about it last time, and we will speak about the same things even today. Okay, so I will wait 1 more minute. If nobody will join, we will start because I see that you're already 28 and 32 in the meeting. So maybe 4 people don't want to join. Okay, I think if it's somebody left that wants to join and it's not here, speak now or right now on the chat. If not, I will press the start button. Okay, start. This is short. Okay, there are just a few questions to settle down better, let's say, some of the notions that we talked about last time. So a standard that defines the specifications for the physical layer and the MACSUB layer. So we're talking about layers in the OSI sieve, let's say. So the physical layer, first layer, and the MACSUB layer, the first sublayer of the second layer. Let's say like this. "24 answers. We wait for 2 more. No, 4 more. Okay, so 13 people responded correctly. No, incorrectly. Sorry, 802.1x. That's not the case. Only 8 people responded correctly. So 802.11. It's the standard, let's say the wireless communication standard up to the second layer. 802.1x is something else that I cannot tell you because all the or almost all this is the idea of the quiz, right? To try to understand better this strange, let's say, protocols or authentication frameworks. So whenever we're speaking about specification of the physical layer in the sense of wireless communication, we speak about what 802.11. And then there are all these letters, if you remember. 802.11 I, that is for some security that it was remember for the WPA, I was saying it's a draft, and WPA2 is going to be this with an I in the back. It's one with the W that means the security of the management frames, not of the data frames. And there are, that's an S, there are a lot of 802.11 and the letter standards, okay? And they all refer to different aspects of the wireless communication up to the second layer. And we know it's up to the second layer because if you remember, all the time we were speaking about MAC addresses, no? The inputs in some, in the key mixing, no? It was the MAC address all the time. It was not the IP address, so we only go to the second layer. For the ones not knowing or not remembering the OSI layering, go back and have a look. It's from networking, let's say. But I think almost everybody got a network course. Okay, web. Yes, but it's not. It's something. It's security. So it's not. Maybe and it's not a standard. Also, the difference between web WPA, WPA2, and everything, what we're studying, and standards that are even some standards related to them, is that the web WPA and so on are the ones that are done by the Wi-Fi Alliance as really implementation on the devices, let's say. So some devices that want to be compliant with all this are using web, WPA, and so on. But it's not a standard in the sense of standard accepted by, let's say, a standardized, a standardization organization like IEEE. Okay, 802.11, it is a standard. It's standardized by IEEE. Okay, IEEE, I hope you know. I think we also talked about that last time, yeah, or maybe 2 or 3 lectures ago. Okay, so it is an organization of engineering and engineers, engineering electronic task force. Sorry, that is EATF. It's another one, but it's an organization, let's say, that is doing standardization. Okay. While web, WPA, and so on are done by the Wi-Fi Alliance. Okay, they are not really standardizations. Okay, so we have the icon in the top. Okay, a standard that defines port-based but also allows more advanced network access control. So think about port-based access control in the network. What is giving us port-based network access control in the network? Okay, so now most of the people replied correctly. If you remember from last time, and also from this activity that I asked you to do, 802.1x is the security framework, let's say, that is the one that is defining the port-based access in the network. And we saw last time in the video when the speaker was referring to physical port access into a switch. But we said, okay, this can also happen, and it is used also for wireless communication. And if you remember, is this architecture that has a supplicant, an authenticator, and an authentication server, right? So with this idea of the let's say of splitting the devices into these three types, allowing the supplicant access control in the network via this access point that is considered to be the authenticator, based on some credentials or upper layer authentication or something like this related to the authentication server. Okay. 802.11 it cannot be anymore because we just said before it's basically what it defines everything in the wireless communication up to the second OSI layer. Okay, we move forward. Okay, it seems we have two and the Halloween power went into the top. A point-to-point protocol. I hope you know what the point-to-point protocol is. It's basically from one entity, let's say, to another entity. So it's from one point to another point, just unidirectional. I mean, can be even bidirectional, but let's say just two endings. Okay, so point-to-point based authentication framework. Okay, so I need to give you a hint. Usually we don't have the same answer several times because it's like the we will have some definition for each of the notions, right? So 802.11 we already talked about, okay? So it's the standard, IEEE standard for wireless communication up to second OSI level. WPA and WEP are security implementations on devices by the Wi-Fi Alliance, which can also certificate these implementations on the devices based on the standards 802.11i, for example, if we talk about WPA2, or 802.11i draft if we talk about WPA. EAPOL, we didn't speak so much about that, but the ones that did the lab, the second lab, saw some messages there. We will talk more about it even today. And we also saw it in the 802.1x architecture, let's say, because there are some messages that are exchanged. And if you remember, the messages between the supplicant and the authentication, not the authenticator. So like, let's say the station and the access point are based on this AAPOL, which what it means, it's AAP over LAN. Okay, it's let's say this kind of again authentication framework and not really a protocol, because it has some types of messages. So it defines let's say some umbrella messages that can contain or encapsulate something else. Because in the end, all this communication, it's an encapsulation of a lot of things, okay? So basically, we can think about, okay, we have this 802.1x architecture with these three entities, let's say, and then we have some EAPOL messages that contain something else that are exchanged between the client, the station, the supplicant, how it's called in 802.1x, and the access point, or the authentication, the authenticator, as it's called in 802.1x. Okay. We will not talk much about this because this is more about transmission, about networking. It's not so much about security, but it's something that you will see. You will see in the four-way handshake. So it's something we need to understand is there. So think about it as some umbrella messages that contain some information. Okay. We keep the top responder. Okay, so an interim towards the IEEE 802.11i standard to improve wireless security. Here I've already given you the answer a little bit before, if you remember. Okay, so now most of the people replied correctly. It's WPA, okay, because we said web was really bad, so they had to find a solution very fast. So WPA is a industry fix, let's say, of web, and it comes before WPA2, which is based on the IEEE 802.11i standard. So we can say the WPA, it's based on IEEE 802.11i draft. It's considered a draft. Okay, so it's not the web, it's not the APOL because we just talked about, it's not radius. I'm not explaining what that is. Okay, we have a change here. And the last question, the fifth question. Defines functionalities for authentication servers and the protocol to allow access them. So it's a protocol that allow us to access, let's say, authentication servers and defines the functionalities of the authentication servers. And it is just an example. There can be others as well. This is just an example. There is one person that doesn't want to answer. Okay, so radius, this is correct. Okay, so if you remember in the 802.1x architecture, we had these APOL messages that were moving between the client and the access point, the supplicant and the authenticator. And then we had these radius messages that were moving from the authenticator to the authentication server. And we were saying, okay, the authentication server can have this radius implementation, let's say. Again, I said this is just an example. We will not study radius in details. There are even others. So I was saying like diameter that is newer and so on. Okay, let's see the podium now, and I will ask the people to write on the chat first place, second place, third place, so that I know how to grant the points. So congrats. So Andrei, please write on the chat the first place, Raresh second place, Stefan third place. Okay. We had a difficult question here, the first one. Okay. You can send feedback if you want. Okay. If somebody has any other questions from this. If not, we move forward. And we talked last time about WPA. Okay, so I'm not going to go over this again. I was saying yes, so it can be considered based on IEEE 802.IE, like a draft. We will move forward WPA 3, which will be based on IEEE 802.11i, okay, without the draft. We saw last time that it's better than WEP because it tries to strengthen the security. And how is doing that? By introducing some better crypto, let's say. So first it's introducing a MIC, a message integrity code, instead of CRC that was not providing integrity at all. Of course, then we also saw that in this algorithm, there are some vulnerabilities. So this Michael, how it's called, algorithm for integrity protection, had some problems. For example, the tag that was supposed to be 64 bits, it's only 32 bits of entropy. So it's like being 32, which means that at least nowadays it can be prone to a brute force attack. 32 bits are really, really low. We also saw that it was very good improvement in the generation of the key, because basically we change the key much often, so it is less exposed. This is a good thing in WPA. It's also a good thing that the IV that was used in WEP was shorter, 24 bits, but now we have this packet sequence number that is 48 bits, so it's double the size, let's say. And we knew that we have a problem if this is resetting, let's say, because in the end, the encryption is a stream cipher. So whenever we reuse the key, we have a problem. We also saw that now the key is different depending on the communication direction, because the transmitter MAC address is also input in the key. So basically, if Alice sends to Bob or Bob sends to Alice, we have different keys. So if the computer sends something to the AP or the AP sends something back to the client, we have different keys and so on. And we also talked about the key hierarchy in the TKIP. So TKIP, if you remember, was this modification of the WEP. So basically this new key mixing with a new message integrity check algorithm. And then we were just using the WEP to be backwards compatible and obtain the, to obtain the ciphertext. And here there were some keys. And if you remember, we talked, okay, there are two types of keys. There were these pairwise transient keys, and there were the group master keys. Does somebody remember what were those used for? So why we have these two type? So why we have a group key and why we have, let's say, a transient key? Yes?
The group key was used for broadcasting messages, if I remember.
Perfect. So the group key was used when the access point needs to send something to everybody in the network, no? Of course, we cannot expect to have one single client connected to the access point. We have several clients connected to the access point. So whenever the access point wants to send something to everybody, we're using this group key to avoid encryption for each of the clients with its own key and so on. And whenever the access point was talking one-to-one with the station, was using these keys. And these keys are kind of split. So basically we start with the master key, and the master key was derived in a 512 bits key. And this key is basically split into four. Two for the APOL messages, what I was saying before, for encryption, sorry, and for integrity. And the second part of this key was used for encryption and integrity within the communication of, the client communication with the access point, the data. And the same for the group key. So whenever data needs to be encrypted, it's encrypted with this key, sorry. And whenever the data needs to be integrity protected, we're using this key. And how they were derived, we were saying it was a key derivation function. We don't really care what's there. It's like an age mark that was getting as input this master key. And the master key, think about it as either something that both the client and the access point have in a personal connection. So for example, you put a password on the Wi-Fi router and the access point, and you put the same password to connect, so the client knows the password. Or it can be this upper layer authentication, for example, with the radio server, no? When it's a challenge response mechanism based on the credentials that are stored on the authentication server, or it can be an APTLS, upper layer authentication, or so on. But think that somehow both of the parties, so the client and the access point, have this key. And then there were two nonces, one that was selected by the access point, one that was selected by the station, and the MAC addresses of the access point and the station, okay, the client. And we didn't say anything else for this. Okay, but how are these nonces known to derive? Because basically this key needs to arrive both at the client and at the access point, right? Because they further use it for encrypting communication. And how this takes place? So how are these nonces sent? How is this PTK computed, and so on? And this is what we're going to speak about today, because this is something that is the same in both WPA and WPA2. And we will continue afterwards with WPA2. And this is also what you are seeing in the second lab, so in laboratory 2. So basically 802.1x, you already know, okay? So again, here I am going to speak less, and you're going to speak more. So what was the 802.1x meaning, let's say, or what do we see on this slide that is totally dependent on 802.1x? If you remember port-based network access control, what we already saw now in the Kahoot, and we knew that there are the supplicant, the authenticator, and the authentication server. Okay, and I was just saying now in the Kahoot, and maybe now it's easier to see, all the communication between the supplicant and the authenticator, it's based on these APOL messages that contain something else. But just let's see them like this, like an umbrella, like a cover, let's say, for something else. And then all the communication between the authenticator and the authentication server, we say this radius communication. So we consider the authentication server to be radius, because this is how WPA considered it at the time. Okay. Okay, and what is happening here? So basically the client, when the client wants to connect to the network, it's sending an initialization request. And it's saying, okay, I want to connect to the authenticator. And the authenticator says, okay, give me your ID. And the client says, okay, here's my ID. And then the authenticator, what can it do? Because we said if we're in an enterprise implementation, so in an enterprise implementation, we need the server. The authenticator will go to the server and say, okay, I got this request from a client and it's putting there some information. What I do? I allow access in the network or I don't for the supplicant. Okay? And the authentication server starts a challenge response mechanism with the supplicant. And if the supplicant, the client, the whatever we have, the device that wants to connect in the network, responds correctly, then the server will say in the radius response, okay, it's success. It's successful authentication. If not, the authentication is failing. Now, all this challenge response mechanism here, it's whatever I was saying is the upper layer authentication that we're not going to speak about so much. So it's basically, it can be some credentials that the supplicant has on the server. So just a username and the password. It can be something based on certificates, like an EAP TLS authentication method. It can be, for example, if the supplicant is, I don't know, a phone, a mobile phone, but do not confuse with what we're going to do in the mobile settings. It can also be this EAP SIM-based authentication, let's say, but it's not the authentication in the mobile network as it is. Anyway, based on something, this upper layer authentication that both the supplicant and authentication server should know or should be able to derive, let's say, in a Diffie-Hellman key exchange based type, if we think about certificates and TLS and so on. At the end, both the supplicant and the authenticator will end up with this PM key. This is the master key. Okay, this is coming from pairwise master key. Okay, so this is where this PMK here comes from. Okay, so this is, let's say, the upper layer authentication. And I said we have here this PM key that can be pre-shared or server-based. And I put here two icons, which corresponds to which type of connection, let's say. Or what want these two to represent here?
I would imagine that the house is for the LAN connection and the building is for WLAN connection.
Yes, but if we think in our settings, so usually yes, it's like this. But if we think in our settings, WPA, we said it can come in two flavors, let's say.
Whether it's business or personal?
Yes, it's called a personal or enterprise. This is just a naming, but it's usually, of course, enterprise for business. So here we talk about personal, WPA personal, where we have pre-shared keys. And that means that basically the authenticator and the authentication server can even be the same. Because as, for example, home, when we use WPA or WPA2, what we have from the provider of the internet connection, we have an access point. And this access point has a password. And this is pre-shared key. So it's a password that both the client and the authenticator knows. So we don't need this authentication server. While in enterprise, it's server-based because we have this server that either stores the credentials, either, as I was saying before, based on some certificates, it's deriving a key based on public key crypto and so on. So basically all the time that we speak about Wi-Fi, we have these two flavors. Personal, where the authenticator and the authentication server are basically, we can consider them the same. We basically don't need this authentication server. And enterprise, where we need this authentication server, and we do have some radius communication here. And based on this is how the PMK, so the pairwise master key, is derived. Okay. Okay, so this is, let's say, the authentication phase, which in the second laboratory you will not see, because there you will have something that is called open authentication. And after this open authentication, it will start a four-way handshake. But if we have, again, a real network where we don't have, what does open authentication means? What do you think? What it makes you the name think about open authentication?
That anyone can authenticate?
Yeah, anyone can authenticate. So basically, I don't have anything here. I don't have a challenge response mechanism. I don't have a password I need to know. I just leave everybody entering the network. Okay, because this is not a port-based network. What is doing? It's like I let you enter in the network in this access point, let's say, which is the authenticator. If you know something, if you respond to a challenge response mechanism, but if it's open, everybody can enter. Okay. So basically, whenever we have a Wi-Fi connection, the first thing is, okay, first we have some beacons that say, okay, I'm here, the authenticator. No, the access point is just sending messages to say it's up, it's there, it's running, and so on, to advertise itself, let's say. Then we have this part of authentication that usually in enterprise implementation is based on authentication servers. If not, it's based on a password that the user knows and it's stored on the access point. The role of this authentication phase is to end up with this PMK, with this pairwise master key for both the client, the supplicant, and the authenticator, the access point. So in this stage, we only have the same PM key here. So what did 802.1x for us was, okay, giving us this structure, let's say, this architecture, let's say, where for personal, I was saying authenticator and authentication server can be the same, so that at the end, both the supplicant and the authenticator end up with this PMK. Okay, how they are doing, I was saying, there can be many ways, but we don't care about that so much. So by now we're just here, to this PMK here. And what we need to do after, to derive the keys, this one, that we split into 4, and then we have the keys that we will use further for the communication, or we will see for the APOL. And how is this done? It's done with the four-way handshake. And the handshake is what you probably are familiar with, no? Probably everybody heard about handshakes before in networking classes, no? So it's basically, again, communication between two entities, up and down, let's say, or forward and no. So and you will say, okay, why is four-way? Because here we see 6 messages. It's called four-way because basically what is more important are the first 4. In the 5th and the 6th, what is happening? What's the purpose, let's say, of the 5th message when you look only at the 5th message? First, who's sending the 5th message?
The access point.
The access point, perfect.
Yeah.
So this is then
the broadcast.
Yes.
Sorry. Yeah, it's the second group key is the one used for broadcasting.
Perfect. So what we see, that's why it's called four-way handshake, because in the first 4 we're doing something we're going to see. That's let's say the most important. While the 5th and 6th, they are also important. I'm not saying they are not, but their goal is to send this group key. Okay, so okay, before continuing, I ask you what we do. We take a break or we don't? Like all the time. I need to ask. If somebody wants to take a break, tell me now or write it in the chat. If not, we continue because I know from last time you want to continue and we finished before. Okay, no opinions, we continue, I understand. Good. So basically in the first 4 messages, the entities, the supplicant and the access point will derive from this master key the transient key, let's say the session key, let's say like this. And then in the last 2 messages, they will consider this group key. So basically the 4-way handshakes takes me here. It's giving me this key. So basically all these 4 here. While the 5th and the 6th message, they're giving me, sorry, this one here, the group key that is used for everybody in the network. And now let's see what they contain. So first, we know that both start with the PMK because we already have it from before, from the authentication. If we have open authentication, this PMK is just generated by random, let's say, from the authenticator, by the authenticator, and just sent to the supplicant here, instead of having a challenge response mechanism. Okay, but somehow they start with something, even if it's just sending it in clear to everybody, it doesn't matter, it's open. Okay. So they both start with this one. Okay. In the first message, who's sending the first message and what is happening in the first message?
The authenticator to the supplicant, the station.
Perfect. And what is containing?
The MAC address of the authenticator, the authenticator Nancy, and I don't know what is the SN.
DSN is a sequence number.
Oh, yeah, sequence number, right?
It's a number, and you will see it in the capture in the laboratory too. It's usually starting from 0 and then it's incrementing. 1 or from 1, I don't remember exactly. I think from 0 and then it's incrementing 1, 2, 3, and so on. And the purpose of the sequence number is also to keep track of pairing messages. So if you can see here, we have the same sequence numbers in the first messages and in the second message. So that means that the second message is a response to the first message because it contains the same sequence number. And then in the third and fourth, we have incremented the sequence number, and again it's the same. So it's known that message 4, it's a reply, a response to the message 3. And now the question is, how do we know that message 3 is coming as the continuation of message 2 in this handshake and not in another?
By sequence number +1. It's the authenticator keep track of the sequence number sent to the station, and if you receive to say the sequence number +1, then they will know that it's a continuation or it's a response to the sequence number they sent.
But if the sequence number is all the time starting from 0? Let's say we have another station here. It's a stranger situation, but let's say that is fake and it's basically, I don't know, it wants to impersonate this one and it's sending a message like again initialization and so on, so that it starts a new handshake. And then it's kind of basically in the same time there are more handshakes and so on. or one is failing and it's starting again, or there's something else that tell us they are paired. Look at the messages and see what message 3 has something else to tell that it's somehow related to the first two.
Oh, it's the non-save of the access point.
Yes, it's the nonce of the access points, eh? And you will also see this in the capture in the lab. Okay, so basically this is how it knows that it's the same. They're paired up. Okay, so coming back.
In this scenario, to say an fake station can mimics both the nonce and the sequence number, so it might respond to.
Yes. If we have a fake access point, we have a problem. That is true. It can make a lot of things, but we have something that he cannot do. Fake authenticator. What? I mean, he needs to be really smart to do that. What is securing the access point?
The message identification code.
Yes. Why? Can you explain a little bit to be clear for everybody?
If I remember correctly, the message with identification code uses a key that they both have, so it can be forged.
Perfect. So here in message 3, we also see that we have a MIC. That needs to be computed by the authenticator, by the access point. And it needs to be computed based on, it's basically the integrity check for all these message 3. So it contains the nonce AP, okay, was even here, but it has a different sequence number. So it has a nonce and a different sequence number. So if something changes, the MIC is considered secure if the AP cannot fake it, cannot forge it. So this should prevent fake AP sending message 3 if the message integrity code is strong, cryptographically speaking. Now, this MIC, we see it somewhere else even before, in message 2. Why we don't have it in message 1? And it's based on what key? It's computed based on what key? I ask both questions together because they are related somehow. So why don't we have a message integrity code in message 1?
It seems that we use the pairwise transient key for generating that.
Yes, which one from this?
The fourth.
This one?
Yes.
This is for the data.
Oh.
We're not transmitting data yet. What we're trying to do with this four-way handshake, we're trying to compute this key, exactly this key, and to be sure that both parties, the supplicant, the client, and the access point authenticator, got it right. But we don't transmit the second.
Sorry, the
first
second one then.
Yeah. So
first.
Yeah, I don't know why here there are no. I need to check if there are really like this, or I just put them in the other way because it's looking strange. MIC and then encryption and then encryption and MIC. Maybe it's like this anyway. It's just splitting of the key. But we are not in the data yet. So by now we're not sending data. We're just of course we're using which key? The APOL MIC key that is used for integrity protection of the APOL messages. Okay? In message 1, why I'm not adding a message integrity code.
I have no key.
I have no key. Exactly. Why I don't have the key? Because again, how is the key derived? It's the first part of this one, but I need two nonces and the MAC addresses and the master key. The master key I have because that was the scope of the authentication phase before this one. One nonce I have because it's me, the access point that I chose it. The MAC address probably I have both because anyway they were communicating even by now, no? Here in the authentication phase. But I don't have what? The nonce of the station. Without the nonce of the station, I cannot compute the key. So I cannot use it to put an integrity protection mechanism here. Though I have a key, I have the master key, no? Why I'm not using the master key to integrity protect this message?
It could not be secure. The attacker could find out the master key.
Yes. I never want to use the master key. Never. As much as I use it in the on the communication, no? As much as I use it, I expose it more. So that's the role, no, of a key hierarchy like here. I derive from a master key some other keys. So that these keys are exposed, but I can change fast, and this key is not exposed. In the normal scenario where we don't have open authentication, this key here is derived directly, let's say, from the credentials stored on the server. I don't want to expose them, even if even there it's a derivation and so on. So I want this master key to be not sent anywhere. And we will see in the mobile networks when we arrive, this master key is going to be something that never ever leaves the phone, never ever leaves the core network of the operator. So I don't want to expose it in general. And here, what I mean, the risk would be high. I expose the master key for what? For protecting a nonce. Okay, but a nonce is something random anyway. No? So, okay, I can have an access point fake that is reusing the same nonce of the access point before and try to use this in a one way to give the fake access point some advantage. But in the end, it doesn't bring me so much because at the end I have a derivation of both nonces. So if the supplicant, the station, is good enough to generate a good nonce here, at the end the PTK will be pseudo-random, will be looking good from the properties of the derivation function. No? So basically it doesn't help me and I don't want to expose it too much. Here, though, after getting the nonce from the access point, the station has everything because the nonce, the second nonce is the one that the station chooses. So it just chooses whatever the station wants. The station already has the nonce of the access point. The station has both MAC addresses because, of course, his MAC address, it knows the MAC address of the access point. It got it from so much communication until now. So the station can compute the PTK because it's basically putting in this function the master key, the nonces, and the MACs. So once it got the PTK, it's just getting the first 128 bits and can use it to calculate this integrity code on the message too. And this is good for the authenticator because it proves the authenticator that it's really coming from that station. Now, why is this, or what is this proving? So for the authenticator, message 2. It's proving that the client knows something. If the MIC is correct.
It's proving that the station knows the master key from which the PTK has been derived and used to calculate the message authentication control.
Perfect. So it's kind of showing, because what is now the authenticator doing? The same thing. So it's getting the nonce from here. It already knows its own nonce from before. It knows the MAC addresses. It knows the PMK. It's computing the PTK. After computing the PTK, it's taking the first 128 bits. It's getting all this message too. It's recomputing the MIC and it's checking. It's the same as the one sent. If yes, I get the messages correct, which means that the station computed this MIC as correct, so it's knowing this PMK for this nonce here. If not, I throw it away. Okay, it might be a chance even here, no? That instead of being the station, it's somebody else that is impersonating buyer, replying attack and so on. But that's really improbable because it needs to use the same nonce as before. So it's based on something that the access point was doing before, selecting this nonce. And then in message 3, what is doing the authenticator? It's saying, okay, I also computed this PTK, and I'm also proving to you that I compute the PTK in the same way by sending a message integrity code to the station. And now what will the station do? It will get the message, it will recompute the MIC on this message, and it will check it's correct. If yes, it means the access point is genuine, it's not fake. I authenticate the access point because the access point knew how to compute it. If not, it's failing. It says, okay, it's not my access point. It's a fake one. It cannot know how to compute the MIC. So by now, both of them have the PTK, and we also have mutual authentication. So the station authenticates the AP because of message 3, and the authenticator authenticates the station because of message 2. And then there's a fourth message, message 4, where the client basically informs the access point that it did install these keys. So it's like an acknowledgement. Okay, access point, I got your message. I agree it's correct. I also authenticate you. So I installed the keys. So from now on, we can both use the same PTK in our communication. Okay, so what we learned by now is where is used this key here. These two keys here, they will be used for encryption and integrity of the data. After the four-way handshake, it starts transmitting. No? Whatever, browsing the internet, seeing, I don't know, a video on YouTube and so on. All this data passing via the access point will be encrypted or and integrity protected if we're in web, no? First integrity protected and then encrypted using these two keys here. Okay, but then we have another key here, the one of APOL for encryption. Where is this one used? So where is the encryption key for APOL used?
in message 5.
Perfect, in message 5. So message 5, again, it's an EAPOL key message. Like I was saying, this umbrella, okay, because all this communication also is happening here between these two afterwards. And we're using here the key, as you can see here. And this is for encrypting message 5. Why do we want to encrypt message 5?
Because it contains the group key.
Perfect, because it's containing the group key. And I don't want the group key, no, to be exposed like this for everybody. It can be exposed for the people that have access anyway to the access point because it's the same internal adversaries. But for outsiders, no. But me, if I'm an outsider, I don't have access to the access point. But I'm just sniffing the communication. If message 5 is not encrypted, I get the group key. I cannot read all the communication of every station with the access point. But when the access point has to do a broadcast, I can read that. So if this would not have been encrypted, there would have been no scope, no aim for this one here. Because everybody could know this one. Okay, so basically this key here is used to encrypt this key here. Send in the 5th message. Here we can notice a sequence number +2, so that we know again it's the next one in the sequence. But it's also okay. There are even others here, notices and so on. It's also a key ID, and the key ID is something that it's giving the identity of a key set. So, for example, the access point can establish several group keys. And then every time it will send the message can say, now I use the key number 2, now I use key number 1, now I use. This is the key ID is on 2 bits, so it can be, there can be up to 4 group keys. Okay, not to use all the time the same, I don't know exactly what for. So basically the group the group key, group transfer key, I don't know how it's called, group transient key, it's chosen by the access point. Okay, so the access point is just choosing it and is sending to the station. Okay, and again, when the station got it, it's sending a message, the 6th message, as an acknowledgement, saying, okay, I got it, I installed it, now we can use it. Okay, so it's just an acknowledgement for the access point to know. So basically, to have an overview of what's happening in a communication, it's something like this. So first time, all the time, let's say, the authenticator is sending these advertising messages. I'm here, this is my SSID. You know what an SSID is, by the way?
It's the broadcast, the name of the access point.
Yes, it's the name of the, let's say, the access point in easy say, okay? So again, I suppose you have some basic notions of networking. So that's the first thing, okay? The authenticator, the access point says, hey, hello, I'm here, this are, and it's sending that, I don't know, at some intervals, you will have one question there in the lab about that. Then the supplicant is saying, oh, I'm here, I want to authenticate to you. It's starting this 802.1x framework authentication where they're using this upper layer authentication, maybe a server, maybe if we're personal, just the password. If we're open authentication, it's just giving something, the access point to the supplicant. The important thing is that after this authentication phase, both the supplicant and the authenticator end up with the master key. And then it's starting the four-way handshake. And in the four-way handshake, from the master key, we derived a one-to-one key. Okay. And after this four-way handshake, we also have the group key. Maybe here I need to put some line or something so that you understand 4 because there are 4 messages and then the other 2 for the group. If you have any other questions or comments here. No. Okay, if not, we move forward to what is called WPA2, because of course, not even WPA is fine, because WPA has some problems. And the problems of the WPA, it's one that, let's say, one is evident. It's very, very simple. And we can see it from here. And I will do this. I don't know how well you can see this one. Anyway, so it's one thing that you can immediately say from here. One type of attack if we consider that the master key is weak. What can we as adversaries do? I'll give you a hint. Oh, no, please.
Many the middle attack.
How a man in the middle?
If derives the key and do to say all the traffic as being to say the station.
How is deriving the key? That's important.
If they know that say the plain key, then they can derive.
It is not knowing, so the adversary cannot know it.
Oh,
even if in open authentication is just sending something random, okay, maybe unclear, maybe you can sniff it. But let's suppose we don't know it, but we know it's coming from a password, and we think that the password might be weak. Let's see.
Brute force.
A brute force, okay? Or a dictionary attack. Why is that possible? What is the adversary really doing? Brute force. What is doing for the brute force?
Trying all possible words, passwords, combinations.
And how is realizing is getting the good one?
Well,
looking at the Mac.
Looking at the Mac. So putting everything, which Mac?
The one that can be sniffed, the AP, it's public. Or the station.
You refer to this Mac?
The Mac used in the transfer, I don't know,
this
the
one?
station or no, the Mac of not the Mac, the Mac.
The Mac, so the Mac address.
Yes.
Okay, it's looking at the Mac, good. It can sniff the Mac, perfect. So basically the adversary knows both this, because it can just sniff the communication. Okay. How is proceeding so that it can do this brute force attack? The nonces are known or not to the adversary?
They should not be known.
They are known.
They're known. Why?
Because they are public.
Because they're public. Huh?
They are not part of the key.
They're not part of the key, but how do I know they are public? They are sent where? In message 1 and message 2. And message 1 and message 2 are? Sent in
Not
clear,
encrypted.
not encrypted. So basically the adversary is sniffing, it's finding nonce AP, nonce station. So these two, he knows. This is not encrypted, it's in clear. You will see in the second laboratory the nonce is in clear. Then the adversary is knowing the MAC addresses, of course, again, everything in clear, it can know, it's communication, you can see MAC addresses. Then it can do exactly what, I don't remember who, I think Vlad said. It can try by brute force, as somebody else was saying, all the values for PMK. So it's deriving all possible values for PTK, and then it's checking, okay, this MIC here is correct or not. Because basically it's seeing all the message. Okay, so it's sniffing all these four. If he knows that the password is is used to derive the PMK, of course that is public as well, how it's derived and so on. It can get to some possible values for PMK. There are many, but not 2 to the 100, not 2 to the 256, because it's coming from a password that is weak. Okay, so it's something that he can brute force. It's getting all these possible PTKs. It's extracting from this PTK the first part, and is checking. Is this the, if I'm recomputing the MIC, I get it or not? If yes, that's the key. So it's getting all PTK. Okay. Now, if the password or the PMK is based on the same password for all the users. So, for example, in the personal implementation, we really have a problem because this PMK is really easy for everybody to compute. So what me as an insider adversary I have to do, I only have to watch on the other's communication when they do the four-way handshake, to sniff the nonces, to sniff the max, and then to derive the key. In enterprise, the PMK is of course different for each based on something else, so it's more difficult to do that. Okay, but that's a problem in WPA because it can be done. Okay, especially for internal. So I don't really have high security for insiders. It's better than web where we were all using the same key, but it's not something that I wish. So I have a problem with the WPA. So we go with WPA2, which comes better to improve this. So basically the WPA2, it's very similar to WPA. It's doing the same. Now I can even put it in full mode. So what it's doing, it's similar to WPA. It has the same, let's say, even here I have a typo, the same type of hierarchy, the same type of keys, the same type of, I don't know, deriving the keys 802.1x, then the handshake. It will still keep the problem from WPA that we were talking about before, because you see that the key is computed the same. But the only difference with WPA is that it's not using WEP anymore. So it's coming with using AES. AES probably everybody knows. If you don't know, you go to crypto course and you you review what AES is. So it's basically the standard used for encryption, advanced encryption standard, used even nowadays for encryption, and which is used in our case for both integrity and confidentiality in two different ways, let's say. So if you remember the operation modes, For confidentiality, it's used in counter mode. And for integrity, it's a MAC that is based also on AES on CBC mode. So again, who doesn't remember the operation modes, go back to a crypto course and check what they are. This thing is called CCMP, counter mode with CBC MAC protocol. This is CCMP. So whatever WPA2 is doing on top of WPA is eliminating the TKIP, which was based on web, that we know was bad, cryptographically speaking, with the AES, which we know is strong. So now we have strong encryption, strong integrity protection. And basically this is what it's doing, okay? So we have, otherwise it's the same. So basically we have the message. The message is first integrity protected with the key, with the MIC key, and a counter block, because even for the MAC in the CBC we have like an initialization vector, let's say a counter, and then this is appended not in web like it was before. So here instead of Michael we have the CBC MAC. Here instead of web we have the AES counter mode. And for the counter mode we have this this IV. Here it's maybe okay, maybe from crypto you were used exactly with the other notion. So I'll put it the counter here because it enters the counter, and the CBC the IV here because it's entering the but I will check this. And then it's the ciphertext that goes out. Okay, so it's nothing nothing different. And now how are these computed? Let's say your desinitialization vectors and so on, they start with I don't know, again they depend on the source address, a package number, then there is the counter, or there is the data length. Yes, here I put them the other way around because the data is important for the CBC MAC. So I will change this one. The counter is here and the IV is here. Okay. And then, okay, there is a flag that is saying we're talking about WPA2. And basically that's all. So that's the difference, WPA2 versus WPA. For backwards compatibility again, WPA2 accepts both the implementation with AES, as here, and the implementation with TKIP, as it was in WPA. So this Michael plus web. Otherwise, we have the same data frame. So basically the data, it is authenticated, but now we will authenticate everything. So also this header, we add, let's say, a header, where in the header we see something, but let's say it's less important. The key ID is the one of the group that we were talking before. Then it's appended to the data and everything is encrypted. So it's very, very similar. Okay, so for me, the most important thing to remember maybe for WPA2 is it allows even to use AES. And officially, of course, whatever devices can use AES should use AES and not go back to the TKIP. Of course, this backwards compatibility introduces some problems. All the time the client can say, or the access point can say, oh, I'm sorry, I cannot really do WPA2 with AES. I need to do TKIP because I just know WPA. And that's a vulnerability, of course, but it's remaining there. Something else you should know as a naming, RSN. RSN is basically the let's say the standard of the more secure network. So it's for us, we can, let's say, use it interchangeable with WPA2 at this point. There is one other difference that I didn't mention. If we compare it to WPA. And at first sight, it can have an impact.
The pairwise transient key has one less element.
Yes. Why? Or why? I mean, where we see that? What is missing or what's happening there?
The data encryption and the data MIC keys have been joined into one key.
Yes. And what do you think? This is good or this is bad? If you think about the principle we were talking before at the first class.
The principle of key separation?
Yes. Very good. If we think about the principle of the key separation, it was saying to us, it's better, no, to have different keys for different purposes. So why would I use the same key for both encryption and integrity? You see here. So basically, I don't have, okay, for the APOL, so the ones that I'm using in the four-way handshake, I have different keys. That's fine. But for the data, I have the same key for encryption and integrity. The same key. Why would I do that? Why would I use the same key for encryption and integrity? Because a crypto result, and we take it as such, in the CCMP mode, so if we're using like this AES encounter mode for encryption and then CBC mode, the CBC MAC for integrity, it doesn't matter if we use the same key or not. So it still remains secure. It's proved to be secure. So we don't gain anything on security if we're using two different ones. So that's let's say a theoretical result that we keep it. And the same, of course, is happening for the group key, because even for the group key, we have the same thing. Whenever a message needs to be sent to the group, it's sent in the same way. Okay, so it's sent as using this only key, both for encryption and integrity. If you have any questions by now. If not, I want to show you just one other thing and then we finish, because anyway, we did not get a break. I want to show you a little bit about the text, and I'm also going to put this online in Moodle, but I want you to see. So basically WPA2, as we were saying, also has a lot of problems. And one of the problems comes from the four-way handshake. Where it is possible, let's say, to reinstall the same keys over and over again because of a vulnerability in the third message, if I remember well, in the four-way handshake. So it's possible to reuse the same key many times. So the attacker can, let's say, make the parties install the key that he already knows. And that was an attack in 2017. Key reinstallations attack, or crack. This is how it's called. And if you look here, you will see a video that is nicely explained how it works. And then you will also see, of course, all the CVEs. Maybe you already know what these are. The common vulnerability and the exposures. So every time that there is a vulnerability found and so on, they're putting it, they're giving it a formal number and so on. And you can see that basically this reinstallation, it can happen in a lot of places. Okay. So mostly for the group key, but it's also having, of course, impact on the peers keys. Okay. You also have the paper. So if you want to read the paper, it's here. so you can read all the details. And there are also some videos that were nice. That was one of them. I think there are even others. You can find all the information about the attack here. Unfortunately, we will not go over the attacks really in detail. You will see that even for WPA3, that we will talk about next time, there's also a similar attack by one of the same authors. There are more authors there, but it's similar, let's say, in WPA3. But it's nice to know because basically it tells us how difficult it is to secure stuff, how easy it is to break stuff sometimes. So it's nice to read if you have more time. This is not, let's say, mandatory for the exam, but it's a nice reading for you to do if you have some spare time. Now, if you have questions from today's lecture. Another thing, this is not the only attack. So after this was out, let's say, some time after was another one that is called Croc. That is basically an attack that was found out as after trying some versions, let's say, of the crack attack, and then they end up with another one that is similar, let's say, but it's a different attack. So don't think it's the only one. I just put their names here, but there are others as well, and I will put the link even there on the on Moodle. So if you have any questions or comments or anything from today's lecture. I did not check today, but I think there were no course project today. Is that true? No. So remember to register for the course project and for the lab project. Let's see, for the lab project, there will be somebody this week. No. So remember also to keep in mind to do that one, okay? Remember to register. So any questions?
I would have one about the course activity from last time that
Yes.
expires today.
Yes.
Is there any indication that we have completed it? I'd only see it in view my attempts. Is that what should happen?
After you finish, you should see the how many points you have. So if that is showing you maximum, then it's done. We can see here who did it. Sorry, who asked the question?
I did ask the question.
Bogdan.
I'm here. Yes. Okay. Thank you.
Yeah. Yeah, so it's here, 100%. Okay, you can retry as many times as you want, but usually for all these activities, so once you try it, sorry, I don't know why it's looking so bad. Once you try it, I just put something. It's written here how much you did. If you arrive 10 out of 10, that it means it's done. 20%, 30%, it doesn't count. So it needs to be fulfilled, okay? And you see it's even taking some points out here. So if you do it wrong, so if we do this one correct, let's say in this one bad, we end up with 0 because it's +1 -1. Okay, any other questions? No, so thank you for attending the lecture today. We meet in 2 days with the people that want to attend the lab on Thursday. I saw there are at least 2 by now that want to present. That's really good. If not with the others next week when we continue with WPA3. Okay, and then we will finish the Wi-Fi and we move forward with other topics in the course. Thanks for attending. Have a nice evening.